right, welcome back. This is chapter 9.1, Introduction to Hypothesis Testing. And let's see, we're off to the races. At the end of this lecture, this chapter, you should be able to correctly formulate and state null and alternative hypotheses. You'll also know what that means. You'll also be able to make and interpret a decision based on the outcome of a statistical test. This is going to be a kind of conceptual overview of hypothesis testing. We'll go through the steps, but I'm going to do it from what I call a 10,000 foot level. It's going to be very general, very high level overview. To help you make sense of things, there's going to refer back to this example. This is also on the handout Hypothesis Testing Sample Problems. This is number 1 on that page. There's others that we'll refer to down the road, but I'll leave it here. It's in the slideshow. You can scroll back and look at it. I will pull it forwards a few times to look at, but if you have it on paper in front of you, it might make things a bit easier. Essentially, this is where we're headed. We're going to see problems like this, word problems like this, as we get into hypothesis testing. This paragraph describes an experimental research study on which someone is using a memory test for which the population mean is 75 and the standard deviation of 6. There's a statement of what this person wants to do. Here he wants to know if smoking marijuana leads to memory impairment, and it describes what the individual does to assess that idea. So he pays 16 marijuana smokers recruited from the public to take the memory test. And there's always going to be results. In this case, I've already figured the mean and standard deviation. In some cases, I'll give you the numbers when you can find the mean and standard deviation. You all know how to do that. We'll go back over that. But here it is, the mean of 70 and the standard deviation of 4. And then there's a question. Do the marijuana smokers have a memory impairment? Test the hypothesis with a 0.05 level of significance. All of that will make much more sense as we go forward, but this is really just an orientation to hypothesis testing. All right, hypothesis testing is essentially an exercise in logic, and that's what we're going to do this week, is work out the logic, and then we'll concretize it with some examples. But this is a logical thinking exercise that you already know how to do, and you already do this every day. We're always trying to think of the world and whether it fits our concept when things happen, whether they fit our conception of the world or not. So think about your worldview, some assumption about the world. And these are so it's hard to see these sometimes because they're so deep grained. But let's just start with one. Let's just say restaurants are good. Most people have this idea that going out to a restaurant is usually a good experience. They're not always good. They're average, right? There's always an average. Sometimes they're really bad. Sometimes they're really good. But you have this general idea that restaurants are good. We hold on to these ideas until we have evidence to the contrary. Something happens that tells us that worldview, that idea, may not be true. We do this all the time. We weigh evidence, and when we see something that's contrary to the evidence, it makes us kind of question our thinking. Formal hypothesis testing is when we're going to use information from samples to make some conclusions about the population. Chapter 6 fits into this because we have to use the central limit theorem. Remember, the central limit theorem tells us that when we know about a population of individuals, we can figure out what the population of sample means is like, the sampling distribution of the means. And we need to know that because hypothesis testing is based upon making decisions on probability. We say things that have a low probability, a low occurrence of happening, are unlikely, and things that have a higher probability, higher frequency of occurring are likely. So we kind of have this idea, we'll hold our worldview, and we look at the probability of our outcome. and consider that. So we need the central limit theorem to figure probability. And you can kind of think where this is going to go. Remember the end of chapter 6, we got into z-scores, right? We can use the z-score to find a probability of a mean. This is a table from the Top Hat chapter that breaks formal hypothesis testing down into, what do we got there? 7 steps. I'm going to make life a little bit simpler and boil this down and not discuss 7 steps. 7 steps is too much. But in my thinking, we can boil this down to 4 steps because some of these go together really well. Step 1 in the Top Hat table is, for me, also step 1. The first step is always going to be state some hypotheses, and they're labeled as H0 and H1. This is where kind of the worldview comes in, where we make some assumptions about the world. The second step is setting up the conclusion, setting up the conditions. Let me see conditions. Conditions under which we will make our decisions. We think ahead of time about what our decision is going to be. And we do this so that we're not swayed by the evidence. Look at it this way. If you got your tax refund and you're going to buy a new television, you know exactly how much money you're going to spend, right? Say you get a $500 tax refund and you can spend up to then $500 on a television. Well, that means when you go to the store to buy the television or look online at televisions, that you're not even going to look at televisions that cost more than $500. Right? Your situation determines really how, in a broad sense, how your decision, how your conclusion is going to be made. If you don't have more than $500, you can't buy a whole range of televisions, right? Your televisions you can buy are $500 and less. You know that going into the shopping experience. With hypothesis testing, we can do the same thing because we specify a level of significance that is analogous to how much money we have to spend. And then we have to set the decision in terms of the particular test that we're going to do. So steps 2, 3, and 4 in the Top Hat is my step 2. And that is down here, choosing the critical value of the test statistic to indicate under what conditions we're going to reject the null hypothesis or not. All of those things for me boil down into one step, and we'll go over that later on. Top Hat step 5 is calculate the test and using data from the sample. We're going to use this formal hypothesis testing framework on a lot of different situations. Test statistics are like golf clubs. They work in very particular situations. They're like tools, right? If you're putting hanging a picture and you've got a nail, you need a hammer. A saw is not going to help you, right? So the statistical tests that we're going to talk about have very limited areas in which they work, but they all use the same framework. So we'll do step 1 and step 2 for every test that we'll do, but step 3 is going to be a little bit different. This is where the math comes in step 3. Top Hat's step 6 and step 7 is my step 4, and that's kind of the wrapping things up. Stating a decision, looking at the results of step 3, Top Hat step 5, looking at the results and making a decision and an interpretation. So this is how I'm going to talk about things. Step 1, step 2, step 3, step 4, because I think they hold together a little bit better, and it's easier to remember 4 things than 7 things. All right, so let's start with the first step, right? Forming and stating the hypotheses. If you've already figured out, we're going to talk about 2 different hypotheses. One's called the null, the other one's called the alternative. Hypotheses are essentially statements about populations, right? Statements about populations. And really, we're always hypothesizing about things that we don't know, right? Why would you hypothesize about things that you do know? So we're always going to be hypothesizing about some unknown thing. Now, in our examples, we're going to always see different populations. They're going to be in different forms. In that example earlier, there were two populations that were discussed. One was known and one was unknown. The known population, right? And we could talk, there it is. We could talk about a mu and sigma for each population. Remember parameters, right? Parameters define the population. So, what were the two populations? Well, in that first problem, sorry, I got it written down in tiny letters here in front of me. There was one population, the one we know about, is the population of individuals that have taken the memory test. That memory test, right, had a population mean and a population sigma. Now, if you look back at the problem, there's nothing, the word population isn't used, but it said, oh, actually it is, right? On a certain memory test, the population mean is 75 with a standard deviation of 6. That tells me something, right? It tells me that there's a population out there of people who've taken this test, and on this test, the mean is 75 with a standard deviation of 6. That's the known population. The unknown population, can't see, I'm just going to go MJ, is what happens if people smoke marijuana for this test? We don't know what their memory performance on this test would be like. We know what people are like without marijuana, but people on marijuana, well, we don't know. That's unknown. So to make these a couple mu's around, I'm going to call this mu sub question mark because I want to point out that it is an unknown population. Over down here, I'm going to call this mu t, or we could just leave it plain old mu and sigma. But I like to use the subscripts to sort out what it is that these numbers belong to. So plain mu and sigma is from the population of individuals on this test. That's how they score. We don't know how people who smoke marijuana score on this test. That's an unknown population. So mu unknown, sigma unknown. The hypotheses we're going to be making are going to really involve both of these populations, right? But we're going to be speculating about this one, mu unknown, and making some logical assumptions about it. All right, so let's start with a null hypothesis. Top Hat, the main author of Top Hat, does this, what I think, backwards, but that's okay. I do it backwards from what they think. The two hypotheses, doesn't matter which comes first, the two hypotheses kind of capture the situation in the problem. I like thinking about the null hypothesis first because that's a statement about the unknown population that we can put some numbers to, some real numbers to. Any hypothesis that we're going to talk about is a statement about a mu. I couldn't get the mu the mu there. Typed in about a mu population mean of an unknown population. So we're really going to be forming hypotheses about what early on the previous slide was mu question mark. The null hypothesis is a statement of no difference. It is a hypothesis that says the unknown population is not different from the population that we do know about. So think of what we got, right? That known population becomes a comparison, becomes a standard, right? If the people who smoke marijuana are not different from everybody else on this memory test, we're going to know what their mean is. We're going to know that their mean is 75, right? Because not different means that it's the same number, right? If I have $5 and the amount of money you have is not different, how much money do you have? That's right, $5. So the null hypothesis is, as a statement of no difference, is a statement that the unknown population is not different from the known population. Notice a logical thing. They're not saying they're the same, saying it's not different. Think of the money example. if the amount of money you have is not different from what I have, it's not saying we are the same, or we have the same $5 bill, right? It says the amount we have is not different. And that's what this null hypothesis is saying. And to finish it off, I always say we mark the null hypothesis with an H and a subscript or notation of a 0. H0, null hypothesis in formal hypothesis testing, written like this. Null hypothesis mu unknown equals 75. As a statement of no difference, the null hypothesis always has an equal sign. Top hat gives us three alternatives: less than or equal to, greater than or equal to, or in some cases they just use a straight up equal, right? Those are all correct, but notice what they have in common. They all have an equal part in there. I always write an equal. I don't like these less thans or greater thans, but technically it's more correct. I don't like them because it kind of hides the equal sign part of it. And it's that equality, that statement of no difference, that matters for the null hypothesis. Let's go back to the worldview memory example, right? Restaurants are good. This is your worldview. This is your assumption. This is what you know about the world. When you go to a new restaurant, right? It's an unknown restaurant. You start with the assumption that your experience there is going to be good. That your experience at the new restaurant is not going to be different than your experience at other restaurants. See the null hypothesis? See the statement of no difference? We take our assumption and we apply it to the new situation. Right? If you're going to go to that new place, you assume it's going to be like any other place and you're going to have the same kind of experience. We always kind of start with a hypothesis of no difference. Where do these things come from? Where does the null hypothesis come from? Well, as you see from the worldview example, it comes from our existing knowledge or experience, but it can come from a reference group. And in the examples that we're going to talk about, it comes from some reference population, some comparison population. All right, so once again, I just want to point this out to you. Here's the problem written out, right? The statement of the null hypothesis is really, right, in this word problem, is there in red, right? This experimental psychologist knows on a certain memory test, the population mean is 75 with a standard deviation of 6. There's some given information. There's our mu and sigma. Mu is 75 with a standard deviation of 6. Now, those are people who are just in the general population. So that led me to, right, according to the thinking of the marijuana smokers. I don't know about them. I have no idea. Whoa, that's a mu. Mu question mark. I have no idea what the mean of the marijuana smokers is. But logically, if they're not different, their mean is also going to be 75. All right, so let's talk now about the alternative hypothesis. The alternative hypothesis is the complement, the alternative, the partner, the nemesis, right? The pair. They're always paired, these hypotheses. The alternative hypothesis is sometimes called the experimental hypothesis, and it captures the situation that the researcher wants to find. The alternative hypothesis is directly contradictory to the null. That's what I mean by opposite. And it embodies what's expected or predicted. Right? For the worldview example, one possible alternative hypothesis is that the new restaurant is bad. Right? So you go in assuming the restaurant's going to be good, but it's possible that it's not good, that it will be bad, right? That would be an alternative hypothesis. There's other alternatives. Maybe the new restaurant is going to be extra good, or maybe you could just say it's going to be different, right? There's a variety of possible alternatives. But when you carry your worldview, you're assuming certain things are in place, that it's going to be good, right? But there's always that alternative lurking in the background. We only know about the alternative after we've collected data, after we have the experience. The alternative hypothesis comes from what the researcher thinks might happen. Right, so it comes from what the researcher thinks might happen. Now, there's a couple different things to think about with alternative hypotheses. Null hypotheses always have an equal sign in them, but with alternative hypotheses, we need to consider directionality. A directional hypothesis states more than or less than the comparison population. So mathematically, logically, let's say logically, we represent these with more than is a greater than, less than is a less than, right? We might think that marijuana smokers score better than average, or we might want to see if they scored less than average. So if there's some kind of wording like that in the problem, it's a directional hypothesis. It's always possible, though, to have a non-directional hypothesis. And non-directional hypotheses just say that things are different, right? And they're vague, right? Think of this. You're a teacher and a parent comes in. Well, let's go the other way. You're a parent and you hear from your child's teacher, oh boy, your kid is different. Doesn't tell you whether your kid is better or worse than the others, right? Teacher's just saying that they're different. All right, let's make this real a little bit. Here's the problem again. The alternative hypothesis in this example is embodied in that red sentence. The researcher wants to know if marijuana smoking leads to memory impairment. So is this a directional or non-directional hypothesis? This one is directional, right? Because it suggests, right, impairment. Impairment is a decrease. Alternative hypotheses are represented with H1. Notice it's a binary situation. That's why we use 0 and 1, right? Alternative hypothesis. Well, we're still speculating about the unknown population of marijuana smokers. We still have the same reference population, right? We know in this test, people without marijuana have a score of 75 on average. Right? This person wants to see if marijuana smoking leads to memory impairment. If that's true, then we should see the mean of the marijuana smoking population, mu unknown, less than 75. I don't know what it's going to be. He has no idea what it will be, but logically, if their memory is impaired, they should score lower on this test. That makes this a directional alternative, and it's appropriate to use the less than sign. All right, the second step. The second step is determining the test and setting the rejection region. But I'm going to stop this slide show here because we're about 20-25 minutes in. There will be a couple of stats garages for you to look at about this. And this corresponds, I'll make a note as to which section of the top hat text this slideshow corresponds to.